start again just in case. Okay. Yeah. So now we know this. We know we're gonna go from liters. Wait, come on. Work. Liters. Why is it not working down here? It works up here. I wonder if there's something. Okay, so it's showing over there, but it's not working over here. Oh, it's slow also. Come on, computer. Okay, hold on. Because it's showing over, it's responding here. It's so weird. Okay, you know what? Let me try to delete this page and then add it again. I don't know what's going on. Some of these computer technological issues I can't even explain. I'm like, it's working. Why is it not working? Okay. It's a little slow. You can see it's kind of still trying to open this page. I've been having some issues lately with some computer stuff, but hopefully, okay. Please work. Yes, it's working now. Okay, so we know our plan will be liters, 2 moles. So liters of given. So given liters, right? 2 mole of given, 2 mole of wanted. Back again, 2 liters of wanted. Okay, so before our conversion was PTBE PT. What's our conversion now? It's a whole different chapter, but it's still stoichiometry. When we go from moles of given to moles of wanted, regardless of what the chapter is, the conversion is the same. It's kind of, imagine this conversion pathway. Imagine it like being you're going somewhere. Okay. So I usually think about it like I live in Dallas. So imagine I live in Dallas and I'm trying to go to Lancaster, where Cedar Valley is. Is there only one way to get there? No. I can use 635. I can use 30. And okay, I should know this. Hold on a second. Hold on a second. I can use Highway 30. You can see I'm one of the greatest at roads. I can use Highway 30 and 45 and then 20, right? The point being, I'm trying to communicate. There's more than one path to get to one place, right? So when you're going from moles of given to moles of wanted, because these conversions are so close to each other, there's usually only one conversion, right? So from moles of given to moles of wanted, the only conversion factor that will get you to that is balanced equation. You can't use another method, right, to go from moles of given to moles of wanted. Now, if you're going from liters to moles of given, you can't use periodic table conversion. That will take you from mass to moles of given, okay? So if you want to go from liters to moles of given, you want to use molarity. So I'm trying to look at the conversion factors like trains or buses. If you're trying to use the A line or the B line or the red line or the blue one, whatever, the different trains take you to different places. So only the balanced equation train takes you from moles of given to moles of wanted, right? And then if you're taking the molarity train, it would take you from liters to moles of given, but it would not take you from mass of given to moles of given. So hopefully that makes sense. I'm really trying to relate this to life outside of chemistry. So hopefully that makes sense. Okay. The trains are the conversion factors taking you from point A to point B. So molarity, balanced equation, molarity. Okay. Back to the problem. With stoichiometry, you always start with a balanced equation. So I'm going to copy that, write this down, paste this down here. And then I have to label what's my given. So I start looking at the dialog here. What volume in liters of 0.150 KCl solution? Okay, what we're looking for is a volume, KCl. So I'll say here, what is wanted is volume. I have no idea what it is. I'm assuming it's in liters of this chemical. So as of right now, this will be my wanted because it's the chemical that was referenced to. They talked about this chemical when they were saying what is the volume of KCl. So that's the chemical that we're looking for. And we're looking for the amount in volume. Okay, what volume in liter? Yeah, of KCl. We're given the molarity 0.150. Molarity 0.150. M is the unit, right? And then will completely react with 0.150 liters. Okay, volume here, 0.150 liters, and then molarity 0.175 molar. Okay, so I'm right here. Solution according to this balanced chemical equation. Okay, so let me look at the numbers given. I'm given all the numbers I need for lead 2 nitrate. I'm giving only one of the numbers I need for KCl. It looks like I'm missing a number for KCl, right? What we're solving for. Am I giving any numbers for the products? No. Remember I mentioned it to you in stoichiometry. In stoichiometry, we deal with two formulas at one time, where one formula is labeled a given. Look at that. It's already labeled here. G for given. The given tends to have the most information. The wanted is usually missing maybe one information we're looking for, right? So here I have highlighted the wanted information we're looking for. Okay, so in our path, we'll start from the liters of given. This one right here. I'll write the liters. I have to write this really small, okay? So 0.150 liters of lead nitrate, PbNO3. Okay, so I'm here. Now I have to use my conversion factor, kind of like the train, to get me to moles of given. So my conversion factor is molarity. So I just use this. My conversion factor is molarity, this second number here. But the way the number is here, it's not written as a conversion factor. So I have to change this to become a conversion factor. I'll rewrite this as, so this is me just rewriting to make it a conversion factor. I can't spell rewriting. Rewriting, right, as 0.175. In the place of M, big M, I write MOL over 1 liter. Remember we said if we want to use molarity as a conversion factor, you have to write it as a fraction. This form is not useful. This is the form we want. So here, I'm going to use molarity in the form I want. I'm going to put the liter part on the bottom. So on the bottom, I have 1 liter. What's the chemical? Lead nitrate. On top, I put this number here, 0.175 MOL. What's the chemical? These are all both lead nitrate, lead 2 nitrate, okay? So as I'm using the numbers, I'm canceling them out, okay? So I use this number in the correct form after rewriting it. Now it says, so I did what? Liters, I use molarity. I'm now here. I'm about to use the balanced equation, the second bus or second train, whatever. The vehicle that would take me from moles of given to moles of wanted. I now look at my balanced equation. That's what B is for. And I have to look at my coefficient. I have 2 here and I have 1 here, right? So this here is molarity conversion. This is a balanced equation. Since I have moles of lead nitrate on top, I'm going to write here moles of lead nitrate on the bottom and then moles of KCl on top. So for my balanced equation, I have 1 here. So I'm going to put 1. For my balanced equation, I have 2 here. So I'm going to put 2 here. Okay. I'm not doing bad at all. I'm actually impressed by myself. I was able to, because I usually write big. Let me make this smaller because it does have to be small. I don't have room for my answer. So that's kind of how I sort of cheat. Not really. I write bigger, then I kind of squeeze it down. Okay. So now I have to use 1 more molarity, right, to get me to the finish line. Yeah. So I'm done with this one here. I need to do 1 more molarity to get me to my desired liters of wanted. Okay. The last molarity is this number here. Just like the other one, I have to rewrite it. So I'm going to rewrite that number, the 0.150, big M. This will be rewritten as 0.150. Once again, MOL on top and then 1 liter on the bottom. But what does this number belong to? It belongs to the KCl chemical. So it's KCl and this is KCl. So let's see. Before I do my last conversion, let me cancel out the units that match diagonally, right? This unit matches with that unit. You can see from the units, just the units alone, not the numbers. Here are the units and the formulas, right? So I'm going to cancel the ones that match. And so based on the ones that remain, I have mole of KCl on top. I'll put mole of KCl on the bottom. Oop, I should write this a little bit further, right? Because I actually have 0.150 mole of KCl. This number here is now written on the bottom, right? Because it has to match diagonally with this one here. Then I'm forced to put the 1 liter of KCl on top. Remember, in dimensional analysis, our desired or our wanted is usually the last one on the top right. Look at that. We're looking for volume in liters of KCl. We have volume in liters of KCl. So we're done with our setup. Our mass will be 0.150 times 0.175 times 2 divided by 0.150. And let's see, 0.150 times 0.175 times 2 divided by 0.150. I end up with 3.5. Is it 3.5? Let's put 3.50 liters of KCl. Okay, so remember, I use molarity twice as a conversion factor. So it's M, balance equation, M. Those are the 3 quote-unquote trains I used to get from liters to another liters. The 3 trains I used to get from mass to mass is PT, balance equation, and then PT. So let's see how they work it out. Oops. Oh, did I do it? Thank you. Let me see. Did I mess something up? Okay, hold on. So 0.150 times 0.175 times 2. Oh, I put something wrong. Hold on. 0.150 times 0.175 times 2 divided by 0.150. Oh, how did I get it? Okay, so now I get points. I don't know how I inputted it at first. Thank you. 0.35, right? And so now I have liters. Okay, let's check it out and see what they get. And once I got down here, I would have realized they got a different number. Thank you. But very good. Yeah. So you see how it is, right? It's not as oh, did I close that one? I thought I had it. Oh, right there. Okay. Yeah, right there. So it's really not that bad, right? The stoichiometry thing, right? 3 conversions, M, B, E, M, and then you got it. It is a wordy problem, but once you can sort through, it's really not that bad. So they talk about types of solutions and solubility. And so here we're talking about 2 major types of solution. I'm trying to see here. Okay, when we're talking about solutions, there are many types, but we're talking about 2 main types. So I want to just kind of summarize this because, yeah, I'll add the page right here. Yeah, very good on the math part. 2 main types of solution. These are the main types that we encounter. Okay, we know how to classify them. We know, I mean, we're about to classify them. We know how to quantify the concentration. We know how to make them solute and solvent, right? And so now we're about to decide, well, what types are there? They're mainly ionic solutions, and then there are molecular solutions. Okay, so for ionic solutions, ionic we're seeing here will be ionic compound plus water most of the time. Molecular solution, we have molecular compounds plus water. So what was the molecular compound again? This is the one that we identify as non-metal for the most part. So example of this, I'm trying to think of a molecular compound solution. Oh yeah, duh, table salt. Sorry, sugar. So sugar plus water. Table salt is the other one. Ionic is table salt plus water. So table salt here is like sodium chloride, right? Ionic because you have metal plus non-metal. Then you add this to water and bam, you get a solution. With sugar and water, the sugar is non-metal. You have six, I'm going to go with glucose. 6 carbons, 12 hydrogens, 6 oxygens. These are all non-metal. Add this to water and you get a solution, right? So what they're talking about here is the how is the solution actually made? When you start off with ionic compound like table salt, the sodium is attracted to the chloride because they have opposite charges, right? They got together, they thought it was real, it was going to be forever, and then they got to a new environment, water. You know how relationships are strong, right? Then the environment changes and all of a sudden that bond is tested. So yeah, sodium and chlorine got together via the ionic bond. Sodium became a positive ion, chlorine became a negative ion, and they had a strong electrostatic attraction for each other. Opposites attract, right? Songs have been written about this attraction. We have an attraction for each other. Yeah, that resulted in the ionic bond. This relationship will last forever, so they said. Then they moved to a new neighborhood where sodium and chloride got added to water. So now we're seeing what's happening here. What we thought was going to be a bond that will last forever is now being tested. Apparently, water, this is water molecule here, has an attraction for chloride ion. There is something called the solvent and solute interaction. So the water molecule here, as you can see, before it was just the sodium and chlorine in a bond together. The water begins to pull the chlorine away from the sodium. Both water molecules are doing that, right? One water molecule pulls the chlorine away from the sodium, the other water molecule is doing that. Well, what attraction does this water have to the sodium ion and chloride ion? We don't learn the proper term in this class, but in 1412, but it's essentially ion dipole interaction. Okay, that's the technical term of this force of attraction. All we know is the water has the power to pull these lovebirds apart from each other. And the affinity they have for water is greater than the one they have for each other. So now you have a competing force. They're trying to pull us apart. Well, they are, right? So while these two are trying to stay together via the solute-solute interaction that we call the ionic bond, we're trying to work it out. The water is trying to pull them apart. In order for a solution to be formed, the water has to win. I don't know why this makes me so sad. It's such a sad story. We try to work it out, it just didn't work out. So now sodium chloride started off as a solid. They were solid together. And then once it gets in water, they're now separated. And as long as the concentration is low, they will remain separate in solution. Okay? They remain separate because the water will just keep them apart. Sometimes your environment can keep you away from a loved one. I'm sorry. This is just taking me back. You can tell I watch too much TV, but yeah. So this is showing you what happens, right? So what we're seeing, we have kind of just walked into the middle of something, right? It's like, wait, what's going on here? What we're seeing here in the purple and green, this is a table salt crystal. So at some point, the table salt crystal was in a geometric shape, like kind of a cube, where all the sodiums that are purple, these are the sodium ions and positive, and the chloride ions are green and negative. They were all stuck together and they kind of moved to a new neighborhood, which was they got added to water. That's a new neighborhood. And they're like, we'll be together forever. This love we have is so real and so strong. And here's the weird thing. the ionic bond is very strong. But once the environment comes in, water not only separates these once very strongly attracted to each other partners, but it keeps them apart. And I'm like, how do people not relate to this stuff? You see how the sodium ion is here? The sodium ion, this process here is called solvation. Okay? If I'm getting a little passionate here because I just have seen this happen in real life with people where the water molecules separate the ions, but not only separate the ions, they're constantly surrounding the sodium ion. So the chances of the sodium ion being free to kind of get back with the chloride ion, it's not going to happen because the water molecules are constantly surrounding it and then kind of preventing it from getting back with the chloride ion. Now, can you make them get back together? Yeah, if you increase the concentration of the ions enough, they can get back together. But you, as a scientist, have to intervene, right? But until then, they stay separate. So you see solvation here around the positive ion, the same thing around the negative ion, and then they remain separate. And you thought they'll be together forever. No, no. Even the strongest can be separated by water molecules. So to tell you right here, each ion is attracted to the surrounding water molecules and then pulled off and away from the crystal when that crystal enters the solution, right? And then as the ions separate from the crystal, they're surrounded by water molecules, and these water molecules insulate the ions from other ions. So they can't even get back together like, hey, listen, I really miss you and I think we should work things out. No, because they're being insulated. And then the result is a solution with freely moving charged particles able to conduct electricity. I mean, yeah, from the scientist point of view, this is great. But from an emotional person like me, I'm like, well, will they ever get back together? In the future, they will when you increase the concentration. Anyway, so once you make that solution, right, now you have separated all the ions. Now the ions are apart. Sodium does not go back with chlorine. They are part in solution. That's okay. These, because they are part, they are able to conduct electricity. Electricity has to do with moving electrons, right? And so as long as the positive and the negative part are not together in an area, then electrons can move between them. So as long as the sodium ions and the chloride ions are separate, the electrons can move between those two ions. So scientists are saying, don't get caught up in the emotion. They're not saying that right now, but that's how I when they're saying this stuff, they're communicating this like it's a good thing. So it's like, don't get so caught up that sodium is separated from chlorine. Realize what this creates. It creates a solution that allows moving electricity. It creates electrons. It creates a solution that can conduct electricity. Electricity. Okay? So now that the partners are separate from each other in their new environment, they can conduct electricity. So they're still kind of communicating with each other by the moving electrons. They're just not together. That's not going to work out. Okay? So we're told, in general, materials that dissolve in water to form a solution that will conduct electricity are called electrolytes. So usually these are ionic compounds, like table salt. Sugar cannot do this. Okay, sugar does not have the ability because sugar doesn't form. First of all, sugar is not ionic compound. It doesn't form opposite charge particles. So these opposite charge particles are not communicating with each other via moving electrons, right? Okay, materials that dissolve in water to form a solution that will not conduct electricity are called non-electrolytes. So this one here are usually molecular compounds, like sugar. Okay, they never break apart. So if they never break apart, they're not trying to use electrons to kind of communicate or stay in touch with each other in solutions, right? And you see that example of this is sugar, and then the salt is right here. So a solution of salt and electrolyte conducts electricity or electrical current. A solution of sugar and non-electrolyte does not, okay? So they're showing you here. Salt solution conducts electricity. Sugar solution doesn't. Okay. Every time I teach this class, I try to get new insight on what the chemicals are trying to do. Okay. So I know chemists try to humanize. I forget what the proper term is. Anthrop anthropomorphic, something like that. When you try to humanize something that's not human, to place human characteristics on it. Yeah, scientists write desire, happy, satisfied, stable, whatever, to these chemicals, right? You're trying to give it human characteristics and human goals and satisfaction and stuff. So even though the sodium ions and the chloride ions are separate from each other, they're still trying to kind of connect with each other the way they can, and they do so via the moving electrons. So because they're separate and that wasn't where they started, these solutions here conduct electricity, okay, as they are sending off the electrons. The molecular compounds, before they get in water, they are a unit, okay? They get in water, they remain as a unit. You see how the water molecules are trying to kind of penetrate, but they have a formation that is solid, right? And the water molecules are lingering around here, waiting for a moment to kind of get in there, and nothing happens. What they have going on in here is solid, right? The sugar molecules, when they're in the water, they're in the same form they were before they got in the water. And the water molecules will always be around them, waiting for an opportunity, but they never get it. And because the molecules of sugar never break apart, they never transmit electrons because there's no need for the molecules to communicate via electrons. They never broke apart, right? So these are non-conducting solutions. Non-conducting. So that's why I'm like, people don't find this interesting. I'm like, man, to me, this is so exciting. I have to tone down my excitement sometimes because people are like, you're too excited. I'm like, this is some deep stuff. Okay. So now that we've gotten into electrolytes, what are they? We want to know more about them. So they're saying here, electrolytes are classified by how they dissolve in water. Remember, electrolytes, we said that they're usually ionic, right? And how they dissolve in water. So let's see. If their dissociation is into ions, they are strong electrolytes. I don't like the way they write that. The ones that have 100% dissociation, they break apart completely. Like the unit they started off with doesn't exist anymore. It's not like a trial separation. I'm talking about break up. Okay, break up completely. So they give an example of strong electrolytes like calcium chloride. When calcium chloride gets in water, before it got in water, it was a unit, right? A compound with one calcium ion like this attached to two chloride ions like that. Each chloride is negative. You see that right? Like there, right? Like that. This is it. And then it got in water. And when it got in water, the calcium ion is now by itself as a calcium ion. And then the two chloride ions are also separate from each other. There, like that. Nothing is attached to the other, right? So the calcium chloride was the starting material. Now in solution form, the calcium ion is by itself, and the chloride ions are by themselves. Even though they're written as 2Cl, this is like a roll call. There's two of them, but they're not attached to each other. All of them are separate. So one unit makes 3 units. Okay, so I hope you see that. One unit makes 3 units, but two are the same kind. Two are chlorine, and then one is calcium ion. Okay. Okay. Then here they're telling you, so this is considered strong electrolyte because when the separation happens, every ion that was together is now separate. What about weak electrolytes? In the weak electrolytes, where this is a messed up symbol right here. This is formic acid. This is the acid. You know, if you have an ant bite, even if you're not allergic, or if you are allergic, when an ant bites you, it kind of itches a little bit, right? That's how you know you've been bitten by an ant. When they bite you, they spit. I mean, it's not like But they inject in the incision, they inject this formic acid so it burns, but to us it feels like an itch, so we scratch. When I heard this, I was like, ew, like bite spit, bite spit. But yeah, the ants put that formic acid in your skin as they bite, right? They usually have an agenda, okay? We're not going into why they're doing all that stuff. Mosquitoes do the same thing too. Mosquitoes bite and spit. It's like, what is up with all these bugs biting and spitting? Anyway, it helps their agenda. But this is formic acid right here. So we are seeing a partial dissociation. The partial dissociation here is hard to see, but if you look at the arrows, these arrows are different. The ones that 100% dissociate, break apart, where everything is broken apart, one-way arrow. Partial dissociation, two-way arrow. You see the kind of like a two-way street? Yeah, top and bottom. What makes this a partial dissociation is the fact that, let's say, to make this easy, let's say we have two compounds, the hydrogen ion, and then the rest of the compound is what? COOH, okay? COOH minus. And another hydrogen ion, and the rest is COOH minus. Let me put three. A hydrogen ion, positive, and then this has to be touching. COOH minus. Okay. But when these get in solution, only one breaks apart. It breaks apart completely, but only one breaks apart. So in this one here, let's say the first one in solution, only the first one breaks apart. The other ones don't break apart. So when these first one break apart, now we have H plus all the way here by itself, and then COOH minus, right? But these other ones remain intact. So we're told here, if we have a weak electrolyte, you have partial dissociation into ions. The compounds still break apart completely, but not all of them break apart, just a couple of them, okay? So you have the extreme break apart, clean break, completely, 100%, called strong electrolyte. You have weak electrolyte, maybe like out of 100 molecules, maybe 3 break apart, and then the rest, 97, are together. And then you have molecular compounds where none break apart. Okay, so you want to know those classifications. Everyone breaks apart. All the molecules break apart. Strong electrolyte. Only 3 out of 100 or couple break apart. Weak electrolyte. Molecular compound is technically a non-electrolyte. So let me see. Oh yeah, here. So they show it to you here, strong versus weak. Yeah, I hate that they do this here because this would have been a good chance for them to kind of illustrate it that way. Okay, you know what I'm going to do? Let me copy this picture here. I just feel like it would have been better for them to put this right here. They use two of a similar type of thing. So let me try to put this here. Okay. I don't know if my goal is really to make things easier. So, okay. So it would have been helpful to do it this way, that according to the picture, so you want to know how to identify those 3 categories here in these 3 pictures. Remember, these are particulate diagrams or particulate level. The level where you're dealing with molecules and atoms and elements. So let me zoom here. Remember, this is sugar. This is table sugar, right? So what we're seeing here is this is classified as a non-electrolyte. That means 0% dissociation. If you look at them, none of them have broken apart. So, how do I write? Can I write thinner? Okay, let me see. Non-electrolyte. Okay, and this is 0% dissociation. Right. How do I know? Let's zoom in and see. Do you see that? All the original molecules are still in the solution intact. So you have nothing breaking apart. This is generally called a non-electrolyte. And we know this is as a molecular compound, right? Molecular compound. Okay, like this. Okay, what about this one here? They label the H plus and the Cl. So you can see no, this is H plus, H plus, H plus. And this is Cl minus, Cl minus, Cl minus. All you can see here is 100% breakup. No one is still together. So here, this would be a strong electrolyte, right? Because we have 100% dissociation or breakup. Dissociated or dissociation, right? 100%. None of the units that were together are still together. Even in the formula, H is with Cl. But in solution, they're not. The water broke them apart. What caused the demise of your relationship? Water. Okay. What about this one over here? This is the original compound, right? Let's see what's going on here. Do we see any broken off pieces? Yeah, they show it to you right here. H plus. There's one broken off piece here. There's two broken off pieces. Ah, so we can say, oh, what am I doing? Hold on. I don't know what I grabbed. We can say here, okay, this is a loose interpretation. This is a weak electrolyte. Okay. How do I know it's a weak electrolyte? Because about 2%, it's not really 2%, but only two of them, 2% dissociated. About 2% broke apart. The rest of them are still together, going strong, right? Like this one here is still together. It's really hard to tell what's together, what isn't. So we just know this one is together because it shows here still together. This formula here matches that one exactly. This is acetic acid, by the way, vinegar, acetic acid. Yeah. So weak electrolyte, 2% dissociated because I'm seeing two free ends. And this one here, all of them are dissociated, all free ends. This one here, it doesn't say it, but the formula in here, there's no tiny pieces hanging around. This is completely C12, H22, O11. Everything is still complete and whole, right? So strong, weak, and none. So we're being told, okay, while we're looking at strong, another example of substances that behave as strong electrolytes, we already said ionic compounds. These are strong electrolytes, okay? They're telling you also acids and bases are compounds that when they dissolve in water, form ions. So in other words, if you're trying to look at the category here, let's see. Strong acids and bases. These dissociate and therefore they are strong electrolyte. Okay, so when the acid is strong, a strong acid is a strong electrolyte. If it's a weak acid, it's a weak electrolyte. That's how I memorized it when I was in school. Strong acids, a strong electrolyte. So here they're telling you hydrochloric acid is a strong acid, so it will dissociate completely. It means 100% in water. HCl will be a strong electrolyte. Acetic acid, vinegar, is a weak acid. Because it's a weak acid, it's a weak electrolyte. So that's why they call it weak. It's not about buffness. It's about ability to ionize, right? It's interesting. There is a thing that the chemical is doing. And to be honest, I don't know if the chemical likes it or doesn't like it. We who are doing the experiment, we are deciding the chemical likes it because it's happening. But we chemicals don't communicate verbally. So they are doing their thing and we are studying them. And then we decide, oh, they like doing this. Why? They do it a lot. I don't know if the chemical likes it. We don't have a psychology for chemicals. So we are just kind of putting our own feelings on them and saying, because they do it a lot, they like to do this. So strong acids like to 100% dissolve in water or ionize in water. Weak acid tend to, like to, prefer to partially dissociate in water. Is this a good thing for them? I don't know. Okay. Non-electrolytes, they do not dissociate in water at all. Is it a matter of them, their preference? Once again, we don't know. So here's another picture showing you the three categories we just learned. Non-electrolyte, weak electrolyte, strong electrolyte. So now that we've seen the theoretical background, How does this play out in the lab? If you were in the lab and for some reason, because it was important to a company, they said, okay, we have a bunch of solutions here. We want you to separate the non-electrolyte from the weak electrolyte from the strong electrolyte, right? Well, how would you know? If you know the chemical formula and you know what is what, right? You could go from that. But if you're in the lab and you have a way to prove your answers, instead of just Googling them, or say the information is not out there on Google. How about that? Let's create a real problem that doesn't really exist, but you know what I'm saying, hypothetical. It's not on Google. So how would you know which is a strong or weak electrolyte? You use this conductivity apparatus. So it's, I mean, you see a bowl, but it's really called a conductivity apparatus. So it's a device designed to test, guess what? Conductivity of what? Is designed to test, do you have ions in solution? And are these ions exchanging secret messages via electrons? Are these ions, having electrons flow in the solution? So this device here will test movement of electrons in solution, which we call electricity, right? Remember, the non-electrolytes are not conducting electricity because the molecule remains intact, so there's no need to transport electricity. So you see, there is no light. No light. The one that's weak, the light bulb is lit, but it's not as lit as the one that's strong. So the light bulb is registering the number of electrons that are being passed from ion to ion in solution. Usually the electrons are going from the sodium to the chloride if it's table salt, right? From the positive ion, so I just say here, from the positive ion to the negative ion, right? That's where the electron is flowing to that. So the more electrons are flowing, the brighter the light. So you can see here, since only a few of the chemicals are releasing electrons, there is some light, but not a whole lot of light. On the other hand, this case here, table salt, where all the chemicals are broken apart. So all the sodium halves, the positive halves, are sending electrons to the negative halves and stuff. You have a bright light. So we know from the intensity of the light that a lot of electrons are being communicated. Are being released between the different ions, right? This will try to communicate with each other. Okay, so we'll talk about, this is like a whole different, I have to talk about this holistically. So it's a whole different section and we'll cover that on Wednesday. But it's about solubility of the different compounds, right? And so yeah, we'll cover that on Wednesday and then keep going. Because your lab this past weekend was about solubility. There should be a video there about how to do the actual lab. So hopefully you have watched that. But this is all I have for today. Let me write myself a future note. Oh, my future self, me on Wednesday, I'll say start here. Okay. And so we'll talk about the solubility rules and different things, areas in chemistry, navigate through. Yeah. I'll have to charge my my pencil so it doesn't die. Yeah. But do you have any questions about the lab or anything?